Okay. Oof. It's live. That's exciting. So you guys can come to the front if you want. It'll be easier later for questions. We're here to talk about recommenders. What really matters in recommenders, indeed. So what I want to talk about today is a little bit about what is recommendation and how the algorithms actually work. But more importantly, especially for DevOps, I want to talk about how it's very, very easy to do practical recommendations with a very easy architecture so that you can build it, as I say here, with things you find around the house in an afternoon. And literally, one of our customers was at a workshop at our site. He left for New York from California. I visited him on Monday, and he'd already built a prototype on their systems. So it should be that easy to build a recommender. And then it should be that easy to move on to the more important tasks of what you do after you have a recommender. How do you make it work well? And of course, we need to talk about how you actually do this, where you find the code. So we'll do that. But of course, there's always too much to talk about. So we may have to surprise just a little bit. So the key parts here are 5 minutes of background and then 5 minutes or a little bit more of theory. And the theory today is called I Want a Pony. Everybody wants a pony, right? Good. You never know with these cultural jokes. Could be different. Okay, so here's the background. Recommenders and machine learning are becoming ubiquitous. You're seeing them all over the place now. It's becoming a dominant form to have user interfaces, especially on web-based systems, which use machine learning and especially use recommendations. The spam filters, Netflix video recommendations and things like that, all obviously use recommendations. People have this impression that underneath it is this very black and white, difficult mathematics. But in fact, I really think that there are much simpler summaries that work, especially as the data gets bigger. The complex aspects of the algorithms can fade away a little bit. Tonight, it's recommenders that we're going to talk about. You've seen them with books and things like that, but you're beginning to see them everywhere. So, for instance, this is a picture of Google Maps, and I did a query for the word Piates in the neighborhood around my office. And it shows, and a little bit of domain knowledge, which you could only know if you live there, is that Piates is a restaurant, one of the classic sort of pseudo-Italian restaurants that you might find. So what they show here is Parcel 104, another restaurant, IHOP, a little bit lower end restaurant, The Demon, another restaurant, Burke's, another restaurant, and Pedro's. They show restaurants. The only technology business here that I see is Oracle. There's a big office right there in the middle of the shopping center. Now, if in nearly the same neighborhood you do a search for MapR, that's these guys, then what you get is medical systems, protein synthesis, rental for offices, instrument builders, lawyers, and most importantly, in this same office, the same building with MapR, what you don't see is the restaurant that's in our building. And you don't see, when you search for this, the tram tracks coming down there. But if I had clicked on the tram station, then the entire route map for the public transit would highlight. If I look for traffic, all of the public transit fades away. So what they're using here literally is recommendation engines to decide which things to show you on a map. And a map is a classic case of too much information. There's far too much information on any good map to show everybody everything all the time. And so Google is now using recommendations as the dominant UI organizing principle. And I think this is a very, very important thing to do. In the past at VIA, we did the same thing with the website. Virtually every link on the website was the result of some kind of recommendation engine. And it gives the site a dynamism that it wouldn't otherwise have and can make it much, much better. So now that you know why we're doing this, let's talk about how it works. I'm going to take as a definition a very general definition of recommendations. A lot of people limit the definition to particular algorithms or particular sorts of things. It has to be ratings, it has to be viewing, or something like that. But I want to take a much more general view, where we learn from a crowd, many behaving things, a crowd of users, we'll call them, but they could be many different kinds of things. They could be other kinds of animals, they could be machines, but they're actors which act on a set of items. I'm going to call the actors users, but they don't have to be. And we want to learn about the crowd because any individual will not have enough behavior to really build a single model for that individual. So we want to learn about the crowd, to learn about concomitant behaviors that are consistent across the cloud. That doesn't mean that you like the same music I do, or you, but it might mean that there are commonalities. There might be some kinds of music that the three of us like in common, and then many kinds of music that we don't have in common. So what we learn about is those common patterns. And then for each person, we look as an overlay of these common patterns. So that's how we learn from the crowd about the individual. Now here's a simple example. Suppose that Alice has an apple and a puppy. That's so cute. And Charles has a bicycle. And then Bob walks in, and he's got an apple that he's tossing up and down. What should we get for Bob? Now, the statistics are not very clear. This is obviously where we need the more complex mathematics. This is not big data yet. But from what we've seen so far, it's reasonable to guess that Bob should get the puppy, because that's what Alice got, apple and then a puppy. And Charles didn't get a puppy, but he only got the bicycle. So that's the fundamental idea. We look for co-occurrence. But there are some difficulties. Suppose we have more users now, and we notice that everybody has a pony. Well, that's what we'd like anyway. Everybody gets a pony. So what are we going to recommend for Amelia? We see that she has a pony, but so does everybody else. So we can learn nothing about Amelia other than she is a user, and so we might recommend common and frequent items there, puppies and apples, just because she is a user and those are common things that users have. But the fact that she has a pony tells us virtually nothing. And that's the key secondary problem. Common items co-occur with way too much. So we want to find the salient co-occurrences and ignore the boring ones, the ones that are there purely because of high frequency. And so what we want to find are the anomalous co-occurrences. So the way we're going to do that is we're going to take log files. We're going to process those into what's called a history matrix. That history matrix is users by items. Process that further to get co-occurrences, which can be arranged in a co-occurrence matrix. And then we want to find anomalous co-occurrences. Here's a log file. Now, most log files are not quite this pretty. They don't have the artist drawing the pictures in there. They only have codes. But you still get the idea. There will be a lookup table somewhere which shows us what's going on. That's the log, the history, and we can rearrange that into a history matrix like this. Each user has a row, Alice, Bob, and Charles, and each item has a column. So you can see right away that apple and puppy co-occurred once. Apple and pony co-occurred twice. Bicycle and pony co-occurred once. Those can be rearranged into this co-occurrence matrix. This is just a matrix multiplication at this point. And we can see all of those co-occurrences that occur there. But we can do a little bit more. We can find out from this which co-occurrences are interesting. To do that, we use something called the log likelihood ratio test, usually called LLR. And the idea there is that the LLR is able to take a set of occurrences with something and without something in this form and decide whether it's an exciting co-occurrence or not. So here we have Apple co-occurred with Alice in the context of Alice with puppy once. Apple occurred in the context of Bob without puppy once. Non-Apple, non-puppy. That was Charles. He had never got an apple, never gotten a puppy. That was once. Now, in more realistic situations, we'll have bigger counts. And if we look at 4 possible cases here, the upper left case, in the context of A, that's the column, B occurs 1.3% of the time. In the context of not A, wherever A did not occur, it occurs 1% of the time. So that's a boring one. That's a co-occurrence that occurs at the same rate we would expect. So we're not interested in that. The one to the right of that, A and B only occurred together, never apart. And so the rate of occurrence of B in the presence of A is 100%. And the rate of occurrence of B in the absence of A is 0%. So that sounds like, in terms of percentages, like a big deal. But in fact, we see we only have 3 users. And so it's a boring thing, again. But it's boring because of lack of data, not for lack of difference. So the first one, we see no difference, but we have plenty of data. The second one, we see a difference, but we have not enough data to conclude anything. But if the not A, not B case were common, much more common, then A and B are both rare, and they occurred together once. And then we begin to say, there's a coincidence to look at. That's an interesting case, but only just barely, because we've only seen them once. And if we see that same sort of thing exactly 10 times more, 10 times as many not A's, not B's, and 10 times as many A and B's, then we have something really to look at. The log likelihood ratio score looks like this for these cases. And it's roughly in the units of standard deviations. 1 standard deviation is boring. 2 standard deviations is not so bad, but it means it would occur in about 5% of the time when there's no connection at all. So if we have 10 million items, 5% of those, 500,000 of them, would show up at this rate. So that's not exciting. 5 standard deviations is kind of like 1 in 40,000. So if we have 10 million items, well, we only have thousands of false positives. This lower right case is 1 in tens of millions, though. So it really is something. We're sure that that's an interesting co-occurrence. So you see how it's pretty easy then. If you just have that one function that can look at the together and apart sort of counts, that's pretty easy. This is part of Mahout. And so we can look at this co-occurrence matrix, and we can reduce all of these counts to 0s and 1s, leaving only the ones where we found significant co-occurrence, or the most significant co-occurrence. Typically what you do is you keep the best 100 or so in a row. Whatever seemed to be the best 100. Here, of course, we have not enough data to really draw many conclusions. I've put check marks on the apple and puppy anyway. Okay, so that's pretty simple. Now, this is the exciting part, and this is where it gets very easy, because all of these first steps are something that standard Mahout software will do. It will take the log files in a suitable form with suitable IDs. It will form the matrices. It'll form the 2x2 things. It'll run the LLR test, reorganize it in a matrix, and output the binary matrices. So up to now, we have Mahout doing the work for us with format translation on the front and format translation on the back. But at this point, we have these. And here what we can do is we can take each row of this significant co-occurrence matrix, this indicator matrix, and we can put it down into a text index as a special field. Now this field, even though it's a text retrieval system, this field is not text. This field is a sequence of IDs. In this case, the ID for Apple. So what happens then, these are the indicators for a particular item. We have ordinary sort of text on that item, title, code, descriptions, keywords, and we have the indicators. So what we do is we take a person's history and we use that as a query. The history queries against the indicator field, Those will be weighted by rarity by the text retrieval engine, and we will get back items that have some or all of the indicators on them. It's that simple. So we have Mahout to do the pre-processing to get us the indicators, and then a system like Solr, or any text retrieval engine you like, to actually do the retrieval, which is then actually a recommendation operation. This is what I call search abuse, because we're using a search engine to do non-search-like tasks. Here's a picture of a LucidWorks running Solr that has musical artists arranged with an indicator field. Here's a zoom on that. And we're running a query which was indicator artists : 2122. That's saying Fats Domino is an indicator, or the Beatles 303 is an indicator. And it retrieves Chuck Berry. Fats Domino gets the early rock, and Beatles kind of accentuate the rock sort of thing. And you can't see it here because it's a very long field, but both 2122 and 303 are in the indicator artists for Chuck Berry. Shazam. In a millisecond, you've got a retrieval, which is a recommendation. And the key is that indicator artist field right there. This, like I said, it's like falling off a log to build one of these systems. You probably already have the retrieval index. All you have to do is update those fields to make the indicators happen. And that's even possible with Solr 4.0 with updatable fields. And so that's cool. But we can do a lot more. We can have much more elaborate behavioral systems. So for instance, suppose we have sample documents which are merchants that have special offers. We can decorate that with many kinds of indicators. Other merchants, what offers the person has done, what industries are found in the person's history. So for instance, in my case, you might find far too many airlines and rental car agencies in terms of industries in my history, and you might know what to locate there. But we would also have location, for instance. And we would have indicators that a certain merchant is a particular favorite within a region. So when I wanted to go to dinner last night, I could have asked what are favorites in Antwerp, regardless of my own interests. So we can do a merged query, which says, in this geolocation, local favorites weekly, and strongly, I want this person's history as indicators. And so the query consists of indicators pulled from the person's history. So we can do these very elaborate systems with multiple kinds of indicators. And here's a little bit about how that works. Here's a specific example where we have two kinds of behaviors that were recorded. One is, what words do people type when they're typing queries? So I might type a particular kind of video that I want to find. I want to find a cat video. I want to find a guitar video. I want to find something else. And then I also might want to watch things. Some of the videos that I engage with would be listed in the B matrix. And so A transpose A, that's the co-occurrence operation on the queries, would give me query recommendations. Doing B transpose B, doing all of those co-occurrence operations on the video watching would give me video watching type recommendations. So I will look at one video page, I would see recommended videos from that page. But B transpose A, instead of doing co-occurrence, doing cross-occurrence from one set to another, can give us a thing called cross recommendations. And in this case, crossing from queries to videos gives us something that looks very much like a search engine, but it's not really. It's really a recommendation engine. It says when people say this, this is what they'd like to see. Here's an example. Paco de Lucia is a Spanish guitarist, and he plays fairly popularized Spanish classical guitar. Now, if you do a text-based retrieval on the million videos that we were using for here, you got Hombres de Paco. It looks like a very good textual match. Paco, Paco, de. 2 out of 3 words of the query, 2 out of 3 words on the text match. It's awesome, according to the text retrieval. In fact, it's horrible because Hombres de Paco is Spanish daytime soap opera sort of stuff. And Paco de Lucia is, at least he says, he's a very serious musician. So this is terrible. But if you take the recommendation search, you get flamenco guitar, you get classical guitar, you get Van Halen doing a little bit of classical guitar in the middle of a concert or video. Here's the real text-based retrievals. It's just Hombres de Paco 400 times. Just appalling 400 times. And here are the recommendation-based things. We have Concierto de las Ideas. We got COD. Now this is an interesting one. COD is a flamenco dance group, and they're dancing the boleria here. So it looks like somebody has engineered knowledge of music. It says COD, dance group. They dance a kind of dance called flamenco. Flamenco is accompanied by guitar. It's practiced in Spain, came out of the Jewish community that also inspired the classical guitar tradition. It's like, whoa, sounds like this amazing ontology built there by humans engineering all of this knowledge. But in fact, all we had is watching people query and watching people play videos. But we did have people then engineer the knowledge necessary to do this query this way. They just engineered it by doing things that they wanted to do anyway. They engineered it by being themselves rather than trying to be experts. And in fact, finding an expert who knows about everything is virtually impossible. When I was looking at music, there were specialized kinds of Polish folk music that Polish people in America listened to, but Polish people in Poland listened to different folk music. You listen to Vietnamese American popular music, it's different on the East and the West Coast. Well, I could have guessed those because I have friends who are Polish and I have friends who are Vietnamese. But the difference between death metal and black metal and Norse metal and other metal, I have no idea. And I made the incautious statement to somebody once and saying, oh, the recommendation engine is drawing a difference here, but that's silly because they're all the same. And they just exploded because to them there was a fantastically huge difference. So we had not enough experts to explain everything that in fact all of our listeners cared about. And do we really care what the experts say, or do we care about what the users say? I'd say the users. And the users are kindly volunteering their time by watching videos, listening to music, and so they're giving us all of this engineering right off the bat. And in fact, we were able to do something else. We put just an icon on the page, and we did cross-recommendation from clicking on the icon to the things that people who click on the icon would like to see. The first 20 people who clicked on the icon got an under construction sign. After that, we recommended for people who clicked on the icon the recommendations for people who clicked on the icon, did this cross-recommendation thing. And the icon that we started with said fast cars. And after a few minutes, the teenage boys who were clicking on the fast cars got to see fast cars and girls in bikinis sitting on the fast cars, just like they wanted. It just took a few minutes for the system to self-organize. So that's kind of cool. But we can actually go into the mathematics of why this all works. And we can see how it integrates. So this is the basic idea. The history matrix times a vector of activity is the fundamental operation of retrieval. It doesn't look like it, but text retrieval engines are doing sparse matrix multiplication. And so if we have a history matrix A and multiplied by history vector, AH, the vector is in terms of items. That's the history of the user that we're searching for. And A translates that into users. And A transpose translates it back to items. So this is the way people think of recommendations. A transpose times AH. AH is users who did, and A transpose said also do this. Now the key thing here is we can do part of that offline, the A transpose H. That's the whole co-occurrence testing that we do with the LLR and the Mahout. That can all be offline, and that learns relationships between items. And we can apply that with a search operation at the last minute. This has the property of moving apart slow parts of the computation So for instance, the relationship between Bach and Beethoven did not change this morning. It's a slow thing. What did change recently are the videos I've just watched or the music I've just listened to. That's H. And so we're doing the fast part of the change in real time. We're doing the slow part of the change offline there. And the recommendations, the cross recommendations we see by symmetry are the same kind of thing. But here's the fun thing. So we can take A and split it into two parts where people interact with two kinds of things. Now, 2 is just a fancy way to pronounce infinity. There's only 3 nice numbers in the world, 0, 1, and infinity. You can explain why you can't do something. This is just the way it is. You can explain this is the way you do something, or you can explain you can do it any way you like. You can't explain here are the 3 ways you do things. It just doesn't work for people. And so when I say 2, what I mean is as many as you like. But it wouldn't fit on the page, especially now. So if we do the A transpose A to these adjoined matrices, the transpose of the adjoined is column adjoined transposes. When we multiply it out, we get 4 products. And when we multiply it by 2 kinds of history, because we have 2 kinds of items now, so the user has a history of type 1 and a history of type 2, then we'll get recommendations in type 1 and type 2 items. But that may not make any sense. So if type 2 are things like location and demographics and age and IP address and so on, those are not things that we reasonably want to recommend. Also things that we could observe but we can't offer for sale or something. We can't recommend those. Those would be type 2 as well. So what we really want to do is have both kinds of history, or all 3 or 5 kinds of history, and recommend a particular set of items. And what this says is we can just add those 2 recommendations together vector-wise, and we get a mathematically correct recommendation. And that's why we can take multiple indicator fields and just throw queries at them all simultaneously. That's why it integrates so nicely with the normal text retrieval engine operation, is because of this sparse matrix multiplication and the addition of scores from different evidence lines. Well, bonus round. This is not actually recommendation theory, but I want to talk a little bit more about some of the practicalities of how you make these things work really well. Once you've got it up, so we've got Mahout running against our log files, we've got Solr sitting there doing retrievals. Okay, well, great, we have a recommendation engine. Now, what should we do? Should we spend time reading the literature, building an ensemble model of 300 different models like they did for the Netflix prize? What should we do? Well, the most significant advance, single advance in recommendation technology over the last 10 years, I contend, is what I call dithering. And this pisses off people in academic research who do recommendation research, because they're working very hard on the algorithms. But it turns out that the simple sort of search-based algorithms get you 90% or so of the score that you would get with the best algorithms at 1/100th of the effort. Literally. The best algorithms involve ensembles of literally hundreds of models. And that's an enormous amount of work to keep it alive, keep it running. Keeping Solr up is like falling off a log. You bring it up and it stays up. It's just easy. So what dithering is a way to make this, help the system explore the possible space of recommendations. Recommendations are a disastrous sort of thing because the training data for recommendations are the recommendations you made yesterday. You recommended stuff, you structured the website a certain way. That's what you observed. Those are the potential things that you might be recommending today. And so if the system was limited to what it knew about yesterday, it'll recommend what it knows about today. It won't recommend things it doesn't know about. And so this issue of exploration and finding out about new things about getting diversity in the recommendations and doing it fast are really the key issues after you get first production running. It's not the last fraction of performance on the recommendation engine. And so what dithering does is it takes a deep result set and reorders it somewhat. It keeps the top items near the top, but some deep items bubble up. And that then will make your performance worse in the short run because you started with the best you could do and you've now reordered it randomly. But it makes it better in the long run because it bubbles up potentially interesting results, serendipitous results, and lets the system learn from that. And a quote from several people that I've advised on recommendations is that introducing dithering made more difference than any other single change that they'd made. So the way it works, the way it doesn't work, is when the real-time recommender writes log files according to what people do, we do the overnight training, and that goes back in. So what we're going to do is we're going to take the normal result ranking and the click-through, where we only get feedback from the first page, and we're going to reorder it. And the way we reorder it is by putting a synthetic score on every item, which is just the rank, the log of the rank, and we add noise, some small amount of noise. Now, the log of the rank goes up quickly at the beginning, and then it goes up more and more slowly. That means a certain amount of noise will have a small effect for low ranks and a large effect on order for the high ranks. And so, in general, the change in the rank as a proportion of the depth is proportional to this particular constant. So if the second and fourth items are reasonably likely to interchange, then the fourth and eighth will be as likely to interchange, eighth and 16th, so that it's scale invariant. It's this log of the depth that gives you the rearrangement scale. Typical values are from 1.5 to 3. And here is an example. Each row here was originally the integers from 0 to 300, or 1 to 300. Here are the first 8 of them after dithering. So you could imagine that each row here is a particular result set that a user might have seen. And so in the first row, you can see that we got results as deep as 15, even though we only showed 8 results. Normally, we just see 1 through 8 on every row. Here we got something from 15 deep. The second row, we got something from 22 deep, and 14, 15, and 10 showed up. And somewhere down here, 33 appeared, 44 appeared. So we would learn about these deep results. We would have an artificial sort of exploration going on in the system. And exploration is good. That's why these systems get much, much better when you add dithering. Now, you can turn the dithering down or up according to what makes the system perform better over time, but having it at all is really, really important. Okay, so in the Mahout project and as part of MapR training, we've been building out a worked example that has all of these components for anybody to try. The key problem here is training data. Nobody wants to put their user logs out in the open because they're liable to get sued the same way that Netflix did for accidentally identifying somebody. Even anonymized logs are dangerous that way. So what we've done is we've built synthetic music listening logs. And if anybody has a better way to do this, I'm thrilled to have it. But this is good enough that you get some flavor of recommendation, and you can scale the log sizes from 1 million users to 10 million users to 100 million users, and as many events per user as you like. And so the history collector takes synthetic stuff or real stuff, pushes it through co-occurrence analysis. Now, to get it through the co-occurrence analysis that Mahout needs, you have to redo the IDs so that they're dense consecutive integers. No big deal. That's one MapReduce step to reformat your logs. The co-occurrence analysis then works in terms of those indexes, and then you have to translate back. Again, no big deal, one MapReduce to translate back. Posting to the search engine, there's a REST interface for that. That gives you a search engine. Then you can have ordinary users come in via standard web tier, and you have a recommendation engine. In blocks, the complete history comes in, does co-occurrence analysis. You can do the indexing inside a MapReduce. That's entirely inside some sort of Hadoop or MapR cluster. And then you can route the search and the web tier directly on the cluster, if you like. So Solr can run against HDFS or directly against the NFS mounts on a MapR cluster. And your web tier can do the same thing. It's really easy to build this. And so soon we'll have that into Mahout. We already have it on GitHub as for commentaries and for people to try out. And I'd love to hear more about how people want to use recommenders and what they want to do. We have 15, 20 minutes. Let's talk about what you guys do. Tell me, recommendations? Anybody have a recommender system or gonna have a recommender system? Yeah. What do you recommend?
Medical analyses for blood samples.
So kind of saying this, he says medical analyses for blood samples. So you're saying, here's what we think is happening with this blood. This is what people have said when your blood looks like this. If you have green blood, somebody said that looks like a Vulcan, that sort of thing, once put on it. We could not comment on it, but somebody said that once. Yeah, so that's a fine recommendation thing. It's a little scary, but it's a really high value one. Scary because whatever you say, somebody's going to be angry at some point, or dead. If you recommend music, some music sounds like it'll kill you, but it probably won't. Not like So anybody else doing a recommender engine? Come now. Or anybody want to? Who works on a web backend sort of thing, where they see consumer behavior? Are you wiggling? Yeah. I get it. I just need to calibrate down. So they're very calm people. Yeah. So he's talking about recommending news items, and the problem there, of course, is that a lot of them are new. But of course, they have inside them old things. We call them words. And so we can recommend words effectively to people, topics that they're interested in. The second thing that I mentioned after dithering was anti-flood, though. And that's a huge issue with news recommendations. Anti-flood is where we try to get rid of near duplicates. And so with news, we want to show you the new development, even though it looks a lot like the old stuff, but only show you one of the old development, or a few, not 100. But yeah, this is a great example. Do you have a system already built? Just starting. But text retrieval is a natural for that, isn't it? And this idea that you could merge together different lines of evidence, what people have watched or engaged in after they start engaging in it, versus the raw text for the cold start, is very attractive. So you might have a kind of a loosey-goosey cold start model in the same retrieval index as the much more refined after 20 people have read the article type of model. So that's exciting. Dithering will be huge there because serendipity on cold items is important. Anybody else? There we go, up there.
You showed an example of a map. How did you take into account similarity like distance? Does that fit in the co-occurrence matrix, or is that a different problem?
So he asks why, when I showed, on my example, I showed location, latitude, longitude sort of thing, and how does that come into recommendations? In the example that I showed, that comes from a customer of ours who is a large bank, and they have an online coupon offers. So your phone will show you coupons for different businesses, especially restaurants. And there they want to show you restaurants that are local to you. So what they do is at the same time you do a recommendation search, they add a geo search limitation. So you might say, add a slight ordering by distance, but more importantly, only show things within a certain radius. Now that's not really quite a recommendation. That's more a filtering on recommendations. There's a couple other things that have to be done there as well, though. One thing that's nice to do is have a regional favorites. So in essence there, you are recommending from location to the restaurant by saying this is a local favorite. And so that's an important aspect of it. But that comes out automatically because what we do is we put indicators on these documents, which are, this is a local favorite top 1%. This is a local favorite top 10%. And then every time we try to get any kind of recommendation, we include top 1% and top 10% indicators in the query. And so everything that is a local favorite also comes along. Now the top 1% are more rare than the top 10%, and so they get higher weight if there are any that match up. And so it all integrates in. But you can do also other things. I think that for most human type activities, geography comes for free because people go to the similar things. If you live in Iowa, you frequent Iowa restaurants, and so you bind them together by the mere physics of where you go. So I don't think you need to explicitly represent it. In fact, I think it works against you sometimes where somebody from Tokyo goes to Iowa and you want a recommendation for them. And there what I think you need to do is like what we suggested here, which is recommend characteristics of the restaurants rather than recommend the restaurants themselves. What cuisine, what kind, what price range, those sorts of things. Because you don't get a straight overlap. Foursquare, he says, does that.
It feels like it because if you go somewhere, they recommend you the types of restaurants that you usually frequent.
Yeah, I couldn't comment exactly on their algorithms, but it's quite plausible that they do these. I know that they did start simple. I'm sure that it's gotten more complex. Yeah, and so the key, of course, is always to start simple on these things. And that's a very simple thing to integrate into text retrieval, so it becomes very simple to deploy. Come on, we got some more. Yeah, over there.
Yeah, it's maybe kind of the same as the news recommendation, but when you have a website and there are for job offers, you could kind of make recommendations which jobs recommend a job for certain profiles of people that look at that site.
Yeah, so he mentions two things. One is user-based search, and the other one is job recommendations. So this is actually, when we do the recommendations with this particular kind of mathematics, we are approximating the same result with user-based or item-based. We're using the user behavior to find all the item things. There are medical applications where user-based recommendations are very, very different because you have a very, very carefully tuned model, say, based on your genetics and test results to find similar users, and we don't have to worry so much about multiple modes of action there. So if we're trying to find how long you're going to survive for a given treatment regime, we want to find everybody who has the same mutations in your tumor. And that can be a very specialized kind of search that is not a matrix multiplication. And so this offline type operation doesn't work. On the other hand, with a lot of these sorts of things, we can get that matrix manipulation to work. Now, jobs are an unusual case because what people say their qualifications are rarely has the literal truth about what you would want to hire them for. I mean, it may be all true things, but it doesn't say why you would want to hire them. And likewise, the job posting does not literally say why you would want to or not want to work in a particular place. So it's a very, very subtle thing. A good human can look at a resume and look at a job posting and say, yeah, that person is a match there. But they're reading secondary characteristics. And so the hope is, and I've seen some of these systems work that way and work well, is that the recommendation system will pick up on when they say this, they mean something like that. So we all know, if you think about somebody who's a Java EE programmer, or Python programmer, or a Scala programmer, you can guess at this time in history, and this will change in the next 2 years or something like that, different personality types, just because of early adopter, late adopter sort of behavior. Who likes complexity, likes managing very large things, likes simple Joule-like properties. So those are personality aspects that lead people to be comfortable in one community or another. And so what we see are keywords that literally mean computer language, but what we understand are personality types. And so we can guess which sort of environment, agile, waterfall, those sorts of things, those people would be happy in. And so that's the sort of secondary inference. Just like the music, we had a musician's name and we got a dance group performing to similar kinds of music. That's the kind of inference we need to make for jobs. So I think this is a real candidate for that. Yeah.
Am I correct then to think that the recommendation engine is actually the easy part in this case, and what you can and want to index is therefore the complicated?
I think the man comes to a very deep truth here. He says the recommendation engine itself is apparently the easy part, and what you want to index, what behavior you want to analyze is the hard part. And this is absolutely true. It used to be true that when you did some sort of machine learning project, that getting the data was 90% of the effort. Well, big data is now bigger than it used to be, and therefore more ponderous and more work to analyze. And the algorithms have gotten easier because as the data gets bigger, two things happen. One is simpler algorithms work well, and also you have a problem in that you have to have very scalable and therefore simple algorithms. So now data acquisition is something like 98 or 99% of your machine learning project. And certainly your first recommendation engine should be very simple and quick to give you time to focus on the data. And we see complexities, because these are humans, very, very complex behaviors. With music, for instance, how long they listen to the music tells you what they like or not. But it's very, very confusing. If they listen to the whole song, it often means they're not listening. If they listen to about 20 seconds, that means it's one of their favorite songs of all time. If they listen to 6 seconds and then skip, it means they hate it. So what's happening there is that their favorite music is something they've heard a lot. They don't need to hear very much before the brain is ringing with that whole response that they wanted from that music. And so they're ready for the next thing. They've had all the fun out of that piece of music already. If they listen to just a few seconds, they were actively trying it and they don't like it. So they've skipped that. Whereas if they've listened to the whole thing, they're not an active user, and so you get very little information. These are the kind of complexities that you need to have to get accurate results. And this paying attention to your users, what are they really telling you, is critical. At VO, the first thing we did is we used clicks on videos. That seems like a reasonable thing. The things they click on and on the search pages or on the recommendation pages should be the things they like, right? It was a disaster. It was the worst thing we'd ever seen. And the problem is we wound up rewarding spammers who would write a great headline and title for content they didn't have. People would see the title and click on it and be fooled. And so what we wound up is building a spam recommender instead of a good recommender. So we had to switch to using 30-second views. So we put a beacon on the video player, so we got 5-second, start, 5-second, 30-second completion sort of events. And that was absolutely critical to getting good performance. But you can't know this ahead of time. Every different kind of user behavior is different. Each user interface gives you different kinds of data. And so you have to learn that. And that really, really is most of the effort. Yeah, we got time for one more. Excuse me. He asks, how do you measure performance? Well, the easiest way and the most accurate way is to measure the happiness of your users. So are they engaging and are they staying on the site longer? Now, beyond that, it gets very, very difficult. And it gets difficult for several reasons. With dithering, we saw how a system, a feature, which makes the instantaneous performance worse, can make the system better. So if we were to take two systems, one with dithering and one without, and do an offline evaluation based on historical data, the one with dithering would be worse. I can guarantee it. It's because of the properties of the random numbers. So offline recommendation evaluation is very, very dangerous. You have to go deeper than it says is true. Secondly, when you have multiple systems live at one time, that's very easy with a search-based recommendation because you just generate different forms of queries. But when you do that, you may wind up with one system that's an explorer and has terrible results, and one system that's an exploiter that uses the explorer's explorations to perform very well. And so you would look at it and you would say, ooh, the exploiter is much better, and turn off the explorer. And now the exploiter falls apart. And so even with live A/B testing, if you allow data to go between the different options, you can have interactions between the systems. And if you don't let the data flow between them, then if you give only a small bandwidth to a test system, it may perform very poorly because it has very little data. So how you tell which one is the best is very difficult to know with great precision. On the other hand, many of the important effects that you get, like add a most recently added published page, or a new music page, or a new whatever page, that's a huge, huge boost in terms of exploration capabilities. That will be an obvious win for your system. You'll see the performance upgrade in terms of user retention, in terms of number of clicks, and things like that. You'll see that immediately. With certain kinds of recommendation errors, for instance, if you move all of the IDs off by one, which surprisingly still works because very often related videos or related whatevers have a range of values, you'll see a dramatic drop in the performance. It won't go to zero, but you'll see a dramatic drop. But again, it'll be in engagement metrics, that sort of thing. But definitely watch carefully, measure many different ways because the problems are quite subtle with evaluation. So I think we can finish just a little bit. We supposedly have 6 minutes left. If there's one or two more questions that are exciting, we can, oh yeah, sure.
How did you come up with the idea of dithering? Because you told that all academic resources told that it's...
How did I come up with the idea of dithering? Well, actually, I was talking to other people who were doing a kind of dithering in signal processing. So in signal processing, you have quantization. But if you add white noise before you quantize the signal, then what happens with high frequencies, it moves between possible code levels that are nearby, and the proportion of time in each step is proportional to where it is between those code words. And so what you get in your ear is you translate the correlated quantization noise into uncorrelated white noise. And so it sounds much better. You've shifted the noise into an imperceptible thing. So the idea there is that you add noise to make a system work better. And I'd also seen adding noise in servo systems. If you have hysteresis on a motor system, then adding noise to the control signal is like tapping the edge of a beaker or something like that that has powder in it. As we tap it, we're adding noise to the positioning of the sugar or whatever we're pouring. Tapping a needle on an old style measurement, or adding noise to the control signal in a servo, all have the same effect. And so it readily became apparent that our system was stuck in a rut. And being stuck feels very much like these control systems, or like quantization noise. And so that was the logic behind trying to add a little bit of noise to lubricate things. And it worked much better than expected. But it was just one of those things. You've got to try a lot of stuff. Okay, well, thank you all for coming. And I'll be around for the rest of the day, and possibly even into the evening. So let's have a beer and let's talk. We've got lots of stuff happening. I've got all kinds of new stuff happening with Mahout, with MapR, with general mathematics. There's just all kinds of things happening in the world right now, and I'd love to talk about them or hear what you guys are doing. So let's do that.